Now, this is an interesting problem. At first sight, it looks really hard. We have x, y, well, that's algebra. We have probability because they're chosen at random when we want to find a probability. We have logs, we have floors, we have so many of these different things. And so how on earth would we even solve this? But let's just take a step back. Let's not panic. We have some algebra, we have some probability. What's a subject we don't have is geometry. So let's use geometry to solve this problem. So real numbers x and y are chosen at this interval from random. What is the probability that the floor of the log of x is equal to the floor of the log base 2 of y? And so I'm just going to try random numbers. Well, first of all, I know that like 1/2 is going to be, or the log base 2 of 1/2 is going to be -1. So the floor of the log base 2 of 1/2 is going to be, well, that's still -1, but the floor of anything that has a less than 1/2, so floor of the log base 2 of some like x, and let's say x has to be less than 1/2 but greater than 1/4. So if we have something like this, less than 1/2, then we know that floor is going to be -2. And similarly, we can have a 1/2 and then less than or equal to x less than 1. The floor of that is going to be -1. Because, well, it's going to be like negative 0 point something if its x is between this range, and taking the floor of negative 0 point something, that's going to give us -1. And similarly here, if x is like in between 1/2 and 1/4, the log base 2 of that is going to be -1 point something, and taking the floor of -1 point something gives us -2. Now this makes it a little bit interesting because now let's actually like bring in the geometry part here. So I'm going to draw like a square. So I'm going to draw this square, and so this is going to be the x-axis. So this is like 0, this is 1. It's probably not going to be a square, keep it, but bear with me here. This is 0, and this is 1. This is the y-axis. So this is the total like space of all the numbers we could possibly pick for x and y. And we know that if x or y are both going to be between this range 1/2 to 1, so I'll just draw that. So I'm just going to draw that. This is 1/2, this is 1/2. So if they're both in this range, that it's going to be like this. I'll draw these lines. If they're both in this range, that means they're going to be equal, because this implies that the floor is -1. And so if y is within the same range, then it's also going to imply the floor is -1. So that's one part. So we have to include this square when we're counting it. But now let's look at the second condition. Well, 1/4 less than or equal to x less than 1/2 gives us that the floor is -2. So I'm going to draw 1/4 here. So 1/4. 1/4. Now let's just extend this again. And we know that if this x and y are also within that same range, then we also have to add in this square because both of their floors are going to be -2. And so we can keep repeating this pattern, so on and so forth, with 1/8 here and 1/16 and so on, and we can keep drawing these in. And so we want to find basically the sum of the areas of these squares that are getting smaller and smaller and smaller. Because these areas, if x and y are both within this region, that means, well, it satisfies, x and y are both satisfying this equality, so that means both of their logs are going to be -1. If they're within this square, they satisfy this. Both of their logs, or both of the floors of their logs, are -2. Here, it's a little different. It's going to be like 1/8 less than or equal to x less than 1/4, or x and y. And if x and y both satisfy that, then we have the log, or the floor of the log is -3, and so on and so forth, such that these things are going to be equal. So now we took this probability problem that involves a lot of complicated algebra and turned it into a geometry problem. Now we just want to find the area of these squares, but if we actually look at this, we can just like keep drawing this so on and so forth. There's actually infinitely many squares. We can keep drawing this so on and so on, like on and on and on. And you want to find the area of this. So let's not panic because, well, we can't find the area of infinitely many squares by just doing it over and over again. So let's just write down, like, see what happens. So this side length is 1/2. This side length is 1/2. So the area of this square right here is 1/2 times 1/2 equals 1/4. Now same thing with this. This side length is 1/4. This side length is 1/4. Area of this is 1/4 times 1/4 equals 1/16. Now let's take a look at this one. This side length is 1/8. This side length is also 1/8. So the area of this square is 1/8 times 1/8 equals 1/64. Now we see the pattern because these denominators keep multiplying by 4. And so this actually becomes an infinite geometric series. So we want to find 1/4 plus 1/16 plus 1/64, and we can keep multiplying by 4. It's going to be 1/256 next because we're going to have 1/16 times 1/16, which gives us 1/256, and so on and so forth. So to find the sum of this infinite geometric series, we'll just use the formula. So it's going to be the formula, the sum is the first number, a sub 1, over 1 minus the common ratio, which is also 1/4, because this is like 1/4. 1/4 times 1/4 is 1/16. 1/16 times 1/4 is 1/64. So we're consecutively multiplying by 1/4. That's the common ratio. So 1/4 divided by 1 minus 1/4, that's the sum. So we do 1/4 over 3/4 equals 1/3. So the area of each of these squares, or I guess the area of all these squares combined, is actually equal to 1/3. But notice we're not done yet, because 1/3 is the area of these squares, so that's the stuff we do want, but the formula for probability is the stuff we do want over the stuff we don't want. So what do we not want? Or I guess not over the stuff we don't want, over the total stuff. So what is the total stuff? The total stuff is the area of this entire square. Area of this entire square, well, this side length is 1, this side length is 1, so it's 1/3 over 1, so I guess the answer is indeed 1/3. So 1/3 is indeed the answer. And the way we did that, we just took geometry first to an algebra problem, and once we actually got this geometry condition, we converted it back into an algebra problem, which is just a simple infinite geometric series.